Okay, thank you, Maria. Thanks for the introduction, and thanks also for the invitation to this great workshop. It's been a pleasure until now to listen to all the great speakers. And a lot of the challenges that I will be discussing, and also actually some of the approaches to deal with them have already been discussed, so that's good. There's quite a fair overlap, so we seem to agree, which is nice. So this is the outline of my talk. I will shortly talk about agriculture and the challenges that agriculture and food production are facing at the moment. And I'll talk about agricultural robotics and their specific challenges, to then dive a little deeper into the challenge of variation and the challenge of occlusion. And I have a little bit of a challenge myself as well. I have quite a large slide deck, so I will discuss a lot of different topics, but all quite briefly. So please, if you have your questions, feel free to ask them afterwards, or contact me by email at some other time, so that we can discuss the details of this work. Good. So the challenges in agriculture and food production. Well, Zero already discusses them at length, but I will just go through them a little briefly. So food production and global agriculture is seeing some big challenges. So first of all, we are getting more and more people demanding more food, needing more feed for the animals, fuel for our cars, fiber for our clothes, etc. Right? But on the other hand, there's a growing scarcity of water, fossil fuel, fertilizers, and also, very importantly, human labor. It seems to be a bit of a contradiction because there are more people, but there's less human labor for agriculture. But this is at least the trend. People are not very willing to work in agriculture. It's a harsh environment, usually very repetitive and hard work. And the last challenge is that there's a big impact of agriculture on the environment, greenhouse gases, waste, all kinds of chemicals, and diseases. So in short, we need to produce more with less impact. One way to do this is to go to more ecological farming systems. So in Wageningen, we're experimenting with strip cropping, mixed cropping systems, instead of having the large monocultures that we currently have with acres and acres of the same crop. We want to go to having many different crops on a field, which is improving the biodiversity. There's also the resilience of the whole field with respect to all kinds of treats and challenges that I just mentioned. But there's a big problem there, is that having these kind of intercropping systems currently requires that there's a lot of human labor involved. And as I said, there's a scarcity of human labor. So we need robotic systems to enable this more sustainable way of agriculture, right? Robots that can do precision agriculture, having the right treatment just at the right moment in time for the right plants. We can enable this ecological farming. We can improve the resource efficiency using this precision agriculture. That's also reducing the pollution. We can reduce waste, but also not only like waste in the field, but also food waste further down in the chain. If we can optimize the growth and development, we can do good predictions about what will happen with the crop when it's ready to be harvested, etc. We can improve breeding at the start. We've already seen some talks about that as well. That can have more efficient plants that can do with less resources. And not unimportantly, we can also solve the labor scarcity, which is then reducing the costs and in the end improves the quality. Right, so robots, this is definitely not the only solution to the general problem of agriculture, but robots can do a fair bit to reach those goals. Right, but to enable robots to work in agricultural fields, there are challenges on their own as well. And we've already seen quite a few of them. There's a lot of variation in agriculture, and not only on the products like we see here, but we want to have robots that can deal with different type of cultivars, and that can deal with all kinds of different weather circumstances, etc. So there's a lot of variation that we need to be able to deal with. There's often incomplete information because it's a complex environment with a lot of occlusions. So we cannot see everything. We still want to make decisions about that type of information. And finally, another problem or an issue challenge is the challenge of safety for the environment, for humans, but also safety for the products themselves that robots are handling. Now, today, I'm not going to talk about the safety aspect, but I'm going to focus on variation and this incomplete information. Now we can look at biological systems, the human being, and I can actually solve with these things, right? So we have very robust perception. We can deal with variation seemingly effortlessly. We can also deal with this incomplete information because humans, all animals actually, are active perceivers. We don't just look at a single static view. Now we move around, right? So we can go to a sense, think, act cycle instead of only sense, think, and then act. This can be a closed loop cycle. And we have soft grippers. So we need also soft actuation in order to deal with the safety issues. Okay, let's look a little bit into the challenge of variation and some of the work that we've been doing towards dealing with this. So variation comes in different forms of variation. First of all, these objects, these are all different tomatoes. They're all tomatoes, but they have different colors, different shapes, and there's a lot of variation there. In the environment, if you go outdoors or in a greenhouse, the environment is causing a lot of variation. Direct sunlight, cloudy days, might be moisture due to rain, might be wet completely. There are different cultivation systems that our robots need to deal with. You don't want to have a specific robot that can only work on one specific type of cultivation system. And preferably, robots can also do several different tasks, right? Now, this is a huge challenge. I'm not going to talk about all of this. We'll talk about some of this type of variations. Now, we've already seen examples of using deep neural networks to deal with some of these variations, and actually they can, right? So they are quite robust, especially if you train them with a robust data set using data augmentation. And they can deal relatively well with the variations in appearances and illuminations. However, this generalization is definitely not completely solved, right? We still have the variation, and I think we've already seen some talks about that as well. Cyril talked about that, for instance. We see that in some of our work. So here, for instance, we look at the generalization of neural networks to other type of cultivars. In this case, it was specifically on broccoli. So the task here is to detect these broccoli heads. This is for a robotic system that automatically harvests these broccolis. And you can see that there are these 3 different cultivars, and they look quite different, right? So what we can all see that are broccoli, but if we train a model only on the Ironman cultivar, well, how well can it actually do on another cultivar, for instance, on the steel or on the emerald crown? Now, we tested that on quite extensive data set using a mask RCNN network that was trained to do the instance segmentation. And we looked at different methods for regularization. So you can do implicit regularization using data augmentation, where you can do, for instance, geometric data augmentation, zooming in, zooming out, doing some stretching of your images. You can also look at photometric data augmentation, changing the colors and the contrast in your images. You can also do explicit regularization of your neural networks, for instance, by simplifying your networks. Deeper networks not necessarily always better, because it might be tending to overfit on your data. So we tested these different regularization techniques. Well, I'm not going to discuss all that data, but what come out is that actually the deeper networks, so the ResNet 101, had a better generalization than the ResNet 50. So making a network simpler in this case was not favorable. And using the data augmentation both geometrically as well as photometrically gave the best results. But then if you look at these 2 figures here, you see that here on the left, we have the results for the cultivar specific segmentation. That has an MIP of 0.76. And this is a generalization to a cultivar that it was not trained on. And you see that there's a drop. It still works. It's not that it completely fails, but that's a drop of about 7% in performance, which is not favorable, of course. Now, what can we do about this? We've already seen that there are other methods to deal with this. Perhaps you can use GANs to work out the differences between these 2 data sets. But what we tried here is to add just a few training samples from the specific cultivar. And the question here is, how many do you need in order to get to your optimal performance again. Right, so here we see that generalization gap. If we add no specific training samples, then we are over here. And we see that only adding 30, 40, well, that's 50 in total, specific training samples from the specific cultivar was enough to get us on the level that we can also reach if we add all the data that we have of the specific cultivar. Right, so this shows that if you have a pre-trained network based on a general set of images of broccoli, you only need a few to make it specific for that cultivar. And this is something that might be useful in practice. If you only need 30 annotations done by the farmer, well, that might be possible. And then this resulted in this robotics system that could detect the harvestable broccolis to a very good extent. As you recall, some precision around 99%. And this is now currently in development by an American company to have the complete automatic harvesting done, and it will be released quite soon. Okay, similarly, we can also look at the generalization to other fields. There's more than only cultivars. And here we looked at, I've already seen a lot of examples of sugar beets and the problem of detecting voluntary potatoes in the sugar beet fields. We also have quite a large background in this specific application. And here we have a large data set of 22 different fields with different systems, different cameras, different cultivars of sugar beets, different cultivars of potato, different soil compositions, different growth stages. So there's a lot of variation in there. And the question is, how well can these networks generalize? In this case, we used the YOLO V3 network, so just standard networks there, and tested how well it can generalize. Now, if you look at these graphs, here, if you look at the start, this is basically if we have a network trained on only a few of the training data sets, five of the training data sets, it shows how well it can perform, generalized to 5 data sets, 5 fields that are in the test data set. And then you see that for some fields it's relatively okay, but for others the performance is not good enough to have an actual system working. But then if we add more training sets, and mind we're not adding more data, right? In all cases, we have 500 images in the training set, which is not a lot, which is just to show the case of what variation can do with your data set. And now we add more training sets of these different fields, but still the amount of images in a training set was set to 500. And you can see that you can improve the performance a lot if you add more variation in your data set, which is especially true for the sugar beets. It's to a lesser extent true for the potatoes. And that's also because there are far less potatoes in the image set. So there's basically 1 out of 10 plants roughly is a potato plant, the rest is sugar beet. And so we don't have enough examples here. There are actually other ways to deal with this. But yeah, the interesting note here is to take that variation, adding variation in a training set helps a lot more actually than it helps to add more images to your data set. Now, maybe you saw that specifically one of these fields here, there was field number T, well, not number, letter T, right, which performed quite poorly. And well, we looked into that a little bit because what turned out that there was one specific training field in one specific field in the training set. Then the performance on field T was actually good, around MEP of about 0.8. But if that was not in, the performance was bad. So looking a little bit on what could cause that problem. So apparently this one training set, set S, very similar in features compared to set T. And we can actually see that as well. Here you see the principal component analysis of the features that we get from layer 36 in the network, so somewhere midway in the network. And if you plot these principal components, you can see that the set T is actually a little bit out of the distribution of the rest of the sets. So this is apparently a set that has a different distribution, and looking into the data, indeed, we saw that there was something specific there. There were a specific type of leaves that were falling from trees in that data set, which didn't appear in the other training sets. So this is follow-up research, but can we perhaps use this so that the network itself can determine if it actually has the right training sets in order to deal with the current field? That's still up for future work, right? So again, here also we tried adding a few samples, training samples from that specific field that we're dealing with, or how can it improve the performance. And you can see that again, it quickly goes up. So if you add some specific training samples from the field that you're really working with, you can improve performance. And again, around 50 images are needed to get to a level which is useful for that working in that field. Okay, so that's still basically designing yourself your training sets. Can we perhaps also use some automatic ways to establish a training set? And this is the field of active learning. Because in practice, what you will often see is that a robot, no matter how large your training set is, it can always or will always encounter a new situation, something that it hasn't seen before, something weird happens. Plants grew differently this season, whatever, can be all kinds of different reasons behind that, but there will be new situations that you need to deal with. So it's important that these neural networks, these methods are aware by the fact that they cannot deal with some of that data. So they need to become aware of how certain they really are about what they're doing. And what we actually see is that most of these neural networks are completely overconfident. They can be very confident making a wrong decision. So can we do something with this? So here we looked into something that's called Monte-Carlo dropout. Again, we took a masked RCNN network. The problem was segmentation, but also classification of broccoli heads. And in the tails of the network, in the box head and the mask head, we added different locations, Monte-Carlo dropout, not during training, that's the normal procedure to make a robust network, but during runtime, right? And then we pass the same image multiple times, for instance, 10 times through this network, and randomly neurons are dropped from the network, and then we see what the output is. And the idea is that if you're really certain about this, if this is an image that the network really can handle, all the 10 times it will result in more or less the same segmentation. But if it's very uncertain about it, it will cause differences. Right, so we took these outputs. This is an example of 3 different outputs. You can see here that the segmentations, they look very similar, but the classification of this broccoli is different. In this case, there was head rot detected. This was a healthy case, and here we see that we have an over-matured broccoli head. So from this, we can calculate our certainties. Certainty on the segmentation, which is a mask and a bounding box certainty. In this case, it's high. A segmentation or classification certainty, so not segmentation, but classification certainty, which we call a semantic certainty, which is in this case low, and then the certainty of the presence of that object being here, which is also in this case very high. Now we can combine that into a general value of certainty. Now, how can we then use this? Well, we start with an initial training data set. This is composed by ourselves. It's a small training set. And then we train a network based on that. And then we have a large pool of unlabeled images that we all run through the network using Monte-Carlo dropout. And for each image, we get an uncertainty measure. And we then collect the n number of most uncertain images that the network cannot deal with, or at least things that cannot deal with, and we add that, we annotate that, and then we add that to the training set. We train a new model, run it again over the pool of unlabeled images, at least the ones that we haven't used yet. Again, we collect new images to annotate, and we add that. Right, and then if we do so, in this case, we want to classify different type of defects on the broccolis. It's not really important what that is exactly at this in this story at the moment. And what we see then is that if we use that, so uncertainty-based collection of new training images, we can see that we really significantly outperform a model that just randomly selects new images from the unlabeled data set pool. Now, in both cases, it goes up. But if we do this based on the uncertainty, we select images that are much more valuable for the neural network to train on, right? So this is a method that it does need human annotations, but it's a method that is becoming aware of its own uncertainty and then asking for help whenever it needs to do so. Okay, I'm not sure how I'm doing with time. Pretty poorly, actually. I will shortly talk about some of the occlusion work. I see that I just really overdid it with a number of slides. Right, so occlusion is one of these other big problems that we've seen. We've already discussed about it. And in this work, we try to quantify what the problem really is. This is not about plants. This is about fish. This is about the classification and counting of fish on a trawler, so on the sea. So we want to have accurate assessments there. But you can see here the system working, and these fish are just they're piled. They come from the nets on a conveyor belt, and then very often piled on top of each other. So we have a lot of occlusions here. And what does that do with our classification? Well, you can see here what it's doing. So we annotated all the fish there, we classified them, but we also annotated the occlusion percentage, or how much of the fish is still visible, running from about 0 to 10% to almost completely covered. And you can see that there's a almost linear, very steep decrease in performance if you have more occlusion. Right? So having this occlusion really becomes a problem at some point. So we need to somehow deal with that. Now I'm gonna, sorry about this, I'm gonna skip this presentation. This is actually work where we try to predict what we cannot see using a neural network. And I'd like to, just for the final notes, to skip to some of the ongoing research, which is on active vision. Right? We've already seen some work where we have robotic systems trying to do phenotyping in greenhouses, etc. And multi-view perception, where you have to take multiple viewpoints on the field as well to deal with occlusions. And those are really good methods. And here we'd like to take it one step further, not only to take multiple viewpoints in a fixed sequence, but to allow the robot itself to reason about what the next viewpoint should be. In this work, it's about the classification of bell peppers into different ripeness stages, where the robot can take additional viewpoints, and it decides on that using basically economical analysis. So it has some form of certainty about its current classification. If it's quite uncertain about this, it will reason about the cost of taking an additional viewpoint, because this takes robot time, and the potential of having a misclassification because of low uncertainty. Now, if we then select the viewpoint, in this case, the viewpoint was selected based on the view that is expected to have most, or the side of the bell pepper where we expect to get most new information because of variation in color. We can see that compared to having a single viewpoint, we can really reduce the cost of this misclassifications. So in 39% of the cases, the system takes an additional viewpoint, and that lowers the amount of misclassifications drastically, and only increases the additional cost for sensing a little bit marginally. This was with 50. These numbers are for 50 bell peppers, by the way. Compared to if you always take a second viewpoint, you can do a little bit better in the classification, but actually the costs are the same. But the cost for sensing then grow up to about more than €1. So that's economically not very feasible. And continuing on that idea of getting more information, this is ongoing work in the FlexCraft program, where we work on next best view planning. Robot takes a viewpoint of, in this case, a tomato plant, and based on what it currently has seen in the environment, but especially what it has not seen, so it's having a voxel representation of space including the unseen parts of space. Based on that, it's planning new viewpoints that can improve the information gain, that are expected to get as much as possible new information, new explored parts of the world, and to get as fast as possible a good representation, in this case a 3D representation of this tomato plant, including all the different plant parts that are there. Okay, to wrap up, so we've seen that we need robots in agriculture to make agriculture more sustainable, but robots deal with challenges themselves, variation and occlusion. And deep neural networks, they can deal with some of that variation, but there will always be new situations, or at least for the foreseeable future. Well, we have seen already other talks with other proposals of how to deal with variations. I add one here, which is an active learning, where the system itself becomes aware of what it cannot do and then asks for help in order to get some additional training data. Now, occluded parts are also a problem, but yeah, I haven't talked about the deep nets that you can use to predict them. But I have talked about the robots that can have the capabilities to actively explore the environment. They can reason about what has been seen, but also what has not been seen, to plan new viewpoints to truly deal with occlusions. So that's it. I would like to thank you very much for your attention and open for questions. And if you want to contact me, my email address is here on